So far we talked about the Bohr model, like your 2D planetary model. But I kind of left off hinting at this idea of the quantum model. So we're going to jump back with Heisenberg. And he had this kind of goal of trying to figure out exactly where an electron was. He had a big problem, though. Well, two problems. The first one was this idea that electrons had a mass. So if you think back, we talked about how that mass was just such a small number, like 10 to the negative 28, that we just kind of assume it's going to be zero. Well, photons, when they hit that electron, because they're so small, it's going to cause that electron to move. It's going to push it, give it some like momentum, right? Now, the second problem is just like the way we make observations, the way we see things. So we don't actually see the object itself. Like if we're looking at that electron, we don't see that electron. What we see is how that electron interacts with the light. So the photon, or that light, comes in, interacts with the electron, it kind of bounces back to our eyes, and gives us that image of the electron. Problem being, once the photon hits the electron, it's going to move it, push it, and give it a new location. So what we're seeing isn't the electron itself, it's where the electron used to be before it interacted with that light. So this problem, this uncertainty problem, we call like the Heisenberg uncertainty principle. Basically, what it says is that we can't know exactly where an electron is and know its speed, or like where it's moving to. Well, that means that we can only ever have like an idea or a prediction of where that electron would be. So like if this was our nucleus for the Bohr model, our normal Bohr, like planetary models, they were just like rings, right? But what Schrodinger was able to do, as with a bunch of math that we're not really going to touch, but he did a bunch of calculations, and he was able to calculate all these different probabilities, all of these like light shaded areas. Those are like probabilities of where the electron could be based on how much energy it had from that observation. And he called this like probability clouds, which now we call like electron clouds. So like 90% of the time, he could predict where that electron was going to be. And this is kind of like the birth of like the quantum model for atoms. But it sounds kind of strange, right? Like how could we not know where an electron is in that model? But through all these calculations that Schrodinger did, he was able to kind of identify or figure out that based on different energy levels and different probabilities, that electron clouds were going to be broken down into these sublevels. Within these sublevels could be further broken down into orbitals. So you're going to hear kind of two words kind of repeated a lot for the rest of this lesson. It's going to be sublevels and orbitals. There are 4 different types of sublevels that we're going to be talking about. So sublevels, you can think about like types, and then orbitals, it's going to be like the number of types of orbitals. But these orbitals are going to be like the 3-dimensional shapes that those sublevels or those types are going to take. But the reason we care so much about like classifying electrons is because electrons are like those things on the outside of your atom. They're the only part of the atom that you can add or remove without changing what the atom is. So that's how like you get like ions, like cations, anions. They're also responsible for chemical reactions. Like they let you bond things together and build other things out of them. So they're super important. And if you think back to our 2D model, that first ring is going to be the smallest ring. And for our rules for drawing, we just said, oh, that first ring, you can fit 2 electrons in it because it's just so small. So we call this the first energy level. So again, energy level, same thing as rings. It's like first energy level is the first ring. Second energy level is the second ring. If you translate it over to the Bohr model. So if we think about the first ring or the first energy level, it's just so small, it only has one sublevel. So again, only one type in that ring. And we call that the S sublevel. So the S sublevel, S kind of stands for like sphere. So if you think about S, it's just shaped like a sphere. If we simplify it, that probability kind of roughly works out to be a sphere, like a ring. But the actual probabilities look a little bit more like that, right? Still basically like a sphere. And every energy level is going to have this S sublevel because it's like the simplest type of shape an atom can have, or an electron can have. So each sublevel, S, is only going to have one orbital, just shaped like a sphere. So if you look at like the first energy level, looks like a regular sphere. The second energy level, like you get two shells, again, you still have that S sublevel. Or if you get three rings, so that three in front means like the third ring, again, you have that S sublevel. It doesn't matter what sublevel you're looking at for S. S can only ever have two electrons in that sublevel. So if you only have one S sublevel, two electrons. In the second ring, your second S sublevel, two electrons. Third, same thing, two electrons. So the S sublevel has one orbital, and every orbital can always fit two electrons in there. A little shortcut I like to tell people is sublevel is a type. Orbital always fits two electrons. It's just different types will have different numbers of orbitals. So S is one, fits two electrons. But once we get to the second energy level, to the second ring, we talked about how that one's a little bit bigger, so you can fit more electrons in there. That second type, or the second energy level, is going to have your S sublevel, but now it also has the P sublevel, or like your second type of orbital. And these are like dumbbell shaped. So if you see, kind of looks like bigger on the outside, kind of smaller once you get in. Almost looks like a dumbbell where you can like grab that handle, right? But that's what like the actual probability clouds look like. There are three types of orbitals within the P sublevel. You have the type that is going to be there we go. You have the type that's going to be in the horizontal or x-axis. You have the type that's going to be in the vertical y-axis. And you have the type that's going to be in that forward back, that's z-axis. Well, if each orbital can hold two electrons, you have two here, and two here. So in total, if there are three orbitals in the P sublevel, and each orbital can fit two electrons, 2 times 3, you can fit 6 electrons in total in that P sublevel. Well, if you have 2 electrons in the P sublevel, or 2 electrons per orbital, 6 electrons in the P sublevel, how many electrons in that second energy level in total? Well, your second energy level has 1 s orbital, and it has 3 p orbitals. Well, 1 s orbital fits 2 electrons. 6 electrons in that p orbital gives us 8 electrons in total. Right, that matches up with the rules for the Bohr model, where the second ring can fit 8 electrons. Once we get to the third energy level, we still have our S sublevel. We have our P sublevel, but now we're adding the D sublevel. In the D sublevel, you can fit 5 orbitals. Each of those 5 orbitals can fit 2 electrons, so the D sublevel can fit a total of 10 electrons. So in the third energy level in total, you can fit 2 from the S, 6 from the P, 10 from D, so you can fit 18 electrons in total in that third energy level. And then the 5 d orbitals, again, you don't have to memorize them. Important idea is just how many electrons fit in that sublevel. In those 5 d orbitals, it's just going to be a combination of directions. So like one would be like some electrons in the in the z-axis and x-axis, some in the y and the z, just different combinations of your different directions. So this is going to be a nice little summary table. It kind of reviews everything. So if we talk about an energy level is going to have a certain number of sublevels in there. And a nice little hint is that the level will also tell you the number of sublevels. So if we look at level 1, it only has one sublevel, just S. If you look at energy level 2, it has two sublevels, S and P. If you look at energy level 3, it has three sublevels, S, P, D. Sublevel 4, you have S, P, D, and F. F we'll take a look at when we start doing examples later on. In the S sublevel, there's only one S orbital. In the S orbital for the second energy level, again, just one orbital type, and you'll see that repeat for everything. For the P sublevel, well, now you have three types, your X, Y, and Z. Once we add the D, you have 5 subtypes, and the F will have 7 subtypes. Now, since electrons don't like being next to each other, like they're both negative in each orbital, right? Because each orbital can fit 2 electrons in there. Each orbital holds those 2 electrons. They have the same charge, so they don't want to be next to each other. So filling them up to the maximum is 2 electrons, and we call this the Pauli exclusion principle. Just says electrons have the same charge and they repel, so each orbital can only fit 2 electrons. That's Pauli's exclusion. It excludes the number of electrons you can fit. Now, jumping into electron configuration, we did a bunch of practice last year. We'll do a little bit of review. So for lithium, you can fit 3 electrons in lithium, right? Number 3 on the periodic table. If you do that shortcut, it has 2 rows. So 1, 2. And it is in the S block. So that's why our S's are there. Okay, so now that we've talked about orbitals and electrons, let's take a look at some practice problems to see more or less what you're going to be seeing. So for this question, it's asking us to write out the electron configuration for silver and to figure out if it's para or diamagnetic. So let's break this into 2 different kind of questions. First one being to write out the configuration. Second one is like those implications of the configuration. So let's deal with the configuration first. Our first step for configuration is just to find silver, which is Ag, on the periodic table. So the reason I want to do that is I need to know the number of electrons, which is based on the atomic number. Configuration is just location of electrons, so I need to know how many they are to know where they're going to go. So for silver, if I check out the periodic table, I can find it right here in the middle, and that atomic number, the little number on the top, is 47. So that tells me silver is going to have 47 electrons. So I'll just note that down, 47 electrons here. Once we figure that out, now we can actually start placing those electrons. If you remember the shortcut for configuration, you can kind of skip this next couple minutes. But if not, I'm going to show you kind of the long way that we got the shortcut from. So our second step is to set up our configuration table. Now this is going to be a simplification of the periodic table. Basically, the only things I care about is the rows. I want to know the types of orbitals. And I want to know the number of columns. That's it. So the actual elements, the numbers, I'm ignoring all of that. These are the only 3 things I want to know. So first, let's do the rows. So on the periodic table, if I number them going straight down, there are going to be 7 rows. So I'm going to set that up. Just going to number 1 through 7 going straight down. Second thing I want to figure out are the types of orbitals. So first year, or last year I should say, we went through and we kind of highlighted the periodic table. And we said that the first two rows, including helium, that was going to be the S block. So I'm going to put S, going straight down because every row has an S block. And looking at it, we only have two columns for each S block. So I'm going to say 2. Now, just a little advance. Each column is going to be an electron we can kind of fill in. So S block having 2 columns, that means we can put 2 electrons in the S block. So that's that number of columns part right there. So after we did S, if I look at the second row, I see going across. Now we're hitting this other section, and that is going to be our P block. So these last 6, I can go ahead and just pull them out. Noticing that the first row did not have any. So I'm just going to take the P block and come straight down. Continuing on, our next one is going to be the middle section here. Notice I'm skipping those 2 boxes in the bottom, but this is going to be our D block. Oh, before that, well, yes, we'll do this. So I'm going to go down 1 again, start with number 3, and put D for each row. If you counted, there should be 10 electrons, or 10 columns in the D block. And then counting for P, because we kind of forgot to do that. There should be 6 columns, so 6 electrons for D. Now doing the last one. Those bottom 2 we skipped, these 2 boxes, are there for the F block. And if you count it across, there's going to be 14 of those. So just like all the other ones, again, skipping 1. So we started with the D in column number 3, or row number 3. So row number 4, we're going to add F. And that's going to be 14 columns, so 14 electrons. So that's pretty much the exact same thing as the periodic table. We're just simplifying it and only including the important stuff or the stuff we need to know. Our next step is to fill in this table. So this table is going to tell us the order that we fill orbitals. So I'm just going to go ahead really quick and copy this. There we go. And then remember that we are trying to figure out, for silver, there are 47 electrons. So I'm going to find a home for all 47. So let's go ahead and do that. When we're filling in this table, I find it a little bit easier for some people if you make like a little line going down the side of your table like that. Because when we're filling this table, we're only going to be able to move perpendicular, like at a 90-degree angle, or like diagonally through that table. So this is how we use it. Starting at the very top, we go through. First thing I hit is 1s. I know in the s orbital I can fit 2 electrons. So if I put all 2, if I subtract, or if I put 1s2, then I can take away 2 electrons from the number we need, and I have 45 electrons left that I got to find a home for. Continuing on, well, the next thing I hit is 2s. So I'm going to put 2s2. That's another 2 electrons. That's 43 electrons left. So continuing on. Notice the next thing I hit is this P. And that is 2p6. So minus another 6. It's going to be 37. And if I continue from there, I'm not going to start a new arrow. I'm going to continue the arrow because I didn't go all the way through my table yet. And if I keep going past that, so I hit that one, keep going past that, next I hit that s orbital. So 3s2. Minus another 2. That's 35 electrons. So if you kept doing that, next I would hit 3p, 4s, 3d, 4p, 5s, 3d, and I would kind of end off there, and I would run out there. I kind of went through that kind of fast, but if you kind of pause the video and you go through it, you will see that should match up. So let me just throw these in here really quick, just for the sake of time. That should be 40. So again, really quick, just to kind of remind you where these numbers are coming from. These lead numbers, well, let's just do it with 40. That number in the front, that is basically just your row number, right? So I'm getting that from like this row right here. The letter is the orbital type. So I got that from right there. And then the number on top, that is the number of electrons in that orbital. And I'm getting that from this bottom number. Oh, it shouldn't be 10. Hold on. 49. There we go. So even though I can fit 10 electrons in the d orbital, if you're going through each one and you're subtracting, once I get to this last step here, I would only have like 9 electrons left. So I can't fit, or I can't put 10 electrons if I only have 9 left. So when I subtracted 9 and I put that last one, it gave me 0 electrons left, and that's how I knew to stop. But you can double check that if you just go through, you add up all these numbers, 2 plus 2 plus 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 6 plus 2 plus 9. That'll add up to 47. So that's how I know I did it right. And that would be the configuration we have. But let's say you don't want to do all this work. The shortcut for this is super easy. So let's go back up here and let's do the shortcut. Oh, let's block that off. Okay. So let's say like I wanted to do the shortcut, right? Well, we saw that we ended off with 4D9, right? So let's figure out if I could like work my way backwards and figure that part out. Well, notice silver, where we found it, we boxed it. If I go across, well, I'm in the 5th row. So I can put a 5. I had to go through the S block 2 times. So 5S 2. Well, we'll just put 5S for now. I moved through 2 squares of the S block. So 5S2. After that, I jumped into the D block. So again, D is a lower energy level, so I subtract 1 from the row. So instead of 5, I put 4. I entered the D block. So 4D. And then in order to get to silver, I had to go through 1, 2, 3, 4, 5, 6, 7, 8, 9. I had to go through 9 boxes to get to silver. And if you take a look at that, well, this 5S2, 49, That's exactly the same as what we got over here, 5s249. My only problem is all of these other electrons. So how do we show those? Well, notice that we ended at 4p6. So is there another atom that has the exact same configuration as all that in red? Well, if I go up one row, I go to the 4th energy level, I go all the way across. Well, let's use a different color, one that you can see. If I go up a row and I go all the way across to like the full shell in that row, I see Kr. Kr is going to be ending in 4p6. So it kind of has like all of those atoms or all those electrons in the same spot that our silver atom has. So I can just put Kr in front of that. And that kind of symbolizes that, oh, all those electrons that we found down here that we didn't show yet, those are all in the exact same spot that Krypton would have them. So we can just put that here. And that's how you find the configuration for silver. Okay, so now that I have the configuration, now we're going to attack that second question, whether or not it's paramagnetic or diamagnetic. All those words really mean is the type of magnetic field that those electrons generate, and that's going to be dependent on how those things are paired up. So what we need to take a look at is going to be, I'll switch over. What we want to figure out is what those electrons look like in that final orbital. So what I want to do is I want to write out electrons for the final orbital. So if my configuration was Krypton 5s2 4d9, what I'm going to do is I'm going to take this 4d9 orbital and I want to expand that orbital and kind of see where all those electrons are at. So I know that in the d orbital, there are kind of 5 types of d orbital. So I'm going to put my 5 arrows or my 5 lines, and each one can take an electron or take a pair of electrons. So my first rule for filling in these orbitals is going to be Hund's rule. So Hund's rule is going to tell me that I need to spread out my electrons within an orbital. So if you remember, like, electrons are negatively charged. So while I'm filling in these electrons, I can put one negatively charged electron there. And I want to spread out my electrons if I can, right? Because negative charges are going to repel if they're too close to each other. So I know I have 9 electrons in total, so 9 arrows. So I'm going to put 3, 4, 5. So Hund's rule just says spread them out if you can. I filled in all the 5 types of d orbital. So now what I'm going to do is now I have to start pairing them up for those last 4 electrons, because I have 5 arrows, 9 in total, so I have 4 left. And in order to figure these out, I need to use Pauli's exclusion principle. Pauli's exclusion. So Pauli's exclusion principle just says paired electrons have opposite spins. So if I do have to put 2 negatively charged electrons together, they're going to do their best to stay away from each other. Well, how are they going to stay away from each other? They're going to spin in opposite directions. While one electron, so if this is like an orbital, right? So maybe that's like that one expanded. I have one electron that's going to be spinning. Let's go back. One electron is spinning clockwise. I'll have another electron that spins counterclockwise, like the opposite direction. So the way I'm going to show that is just an opposite directed arrow. So I need to do 4 of those. So I do 1, 2, 3, 4. So with that, I have all of my electrons filled in, all 9 of them. So now we're going to kind of take a look at the breakdown of my electrons. And I'm basically just looking for, let's move that up. I look for lone electrons. So this is how we're going to figure it out. Paramagnetic it just means that I have at least one unpaired electron. And if I have one unpaired electron, that means I have like an open space